Today we are to discuss the analysis of indeterminate truss using virtual work method. So for example, we have this truss a little bit as shown. And let us assume that we have the area, cross-sectional area of each bar and the modulus of elasticity to be constant. Okay, so how to determine or how to start the analysis of indeterminate trusses using the virtual work method? First, we need to determine the degree of indeterminacy. So we have, to determine the degree of indeterminacy, previously for truss, we have the number of bars plus the number of support reactions. Is it equal, greater than or less than twice the number of joints? So how many bars do we have? So we have 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we have 9 bars. Plus, as you can see, we have supports A and D are hinge supports. So for hinge support, we have two support reactions. So let's say vertical reaction at B. Let's say the horizontal reaction at D is to the right. And the vertical reaction at A. And we have the horizontal reaction at A. So as you can see, we have 4 support reactions. Is it greater than or less than or equal to twice the joints? How many joints? 1, 2, 3, 4, 5, 6. We have 6 joints. So this is now 13 is obviously greater than 12. Our degree of indeterminacy is obviously 13 minus 12. That is first degree. We are lacking with one equation for a reason. We have 4 support reactions and 4 support reactions, and we have only 3 equations of equilibrium. So what causes the degree? What causes the indeterminacy of this truss? So we have an excess support reaction. If we have an excess support reaction, it only means that this truss is indeterminate. And this indeterminate externally. Since the cause of indeterminacy is an excess support reaction, this truss is indeterminate externally. If we have an excess bar force or excess bar member, that is considered to be indeterminate internally. So our first step for the virtual work method, we need to choose our redundant. So we have, let us choose our redundant. That redundant will be the excess support reaction. So how many reactions do we have? Meron tayong 4, so we have 4, AB, AH, DH, and DB. We may choose one of them since the cause of indeterminacy is an excess support reaction. So I'll be choosing DH as our redundant. So it says we have a DH. Then our compatibility equation, so for the compatibility equation, there is a delta, or this is the deflection of the frame or the truss due to real load, plus the deflection of the truss, this is due to the unit load, then multiplied by the redundant should be equal to 0. So this is from the concept of virtual work method. So deflection of the primary truss due to real load, deflection of the truss due to a unit load, then multiplied by the redundant equal to 0. Since in that point or in that redundant, let's say or in this point, for example, we are choosing point D, there's no actual deflection, or the summation of work in this joint is basically equal to 0. So what is the equivalent of the deflection due to real load? This is the summation of S, let's say S, that is the summation, this is the axial force due to real load. You have U, the axial force for all members due to unit load, multiplied by the length, divided by the area, times the modulus of elasticity. You have F, the deflection of the primary truss due to unit load. So that is the unit load, or summation of axial force due to unit load, the axial force due to unit load, the length, divided by the area, times the modulus of elasticity. Okay, so since we are choosing DH to be the redundant, okay, we are to remove that. Okay, so how to remove this horizontal reaction at joint D? We may change this hinge support into a ruler to remove its horizontal resistance. So changing the support at D into a ruler to remove the redundant DH. Now we have only one reaction at point D, that is the vertical reaction. That makes this truss determinate. So magiging determinate na siya. We can compute for the axial force for all members. So we may have, this is the summation of moment at joint A equal to 0, clockwise moments to be positive. We have this is 60 times 3 plus 120 multiplied by 6 plus 30 times 4 minus the vertical reaction at D multiplied by 9 equal to 0. So we have the vertical reaction at point D. So we have 100. So the 113.333 kilonewtons. So that will be the vertical reaction at point D. Summation of forces vertical equal to 0, upward forces to be positive. So we have A vertical plus DB is 113.333 minus the downward loads 60, then 120 equal to 0. So you have the vertical reaction at A is equal to 66.667 kilonewtons. So those are the support reactions. So since we have a horizontal load of 30 kilonewtons and AH is the only horizontal resistance of the truss, we assume that the A horizontal is the same as 30 kilonewtons. Okay, so we have the support reactions. We are not to compute for the axial forces due to, first, due to real load. So analyze as already a determinate truss. So we proceed at joint A. Let us compute for the axial force for all members. So we may do summation forces vertical equal to 0, upward forces to be positive. So this is, we have 66.667 less vertical component, that will be 4/5 of the axial force for member AB equal to 0. So we have the axial force for member AB. It's equal to 83.333 kilonewtons, and this under compression. Yeah, for member AB. Then I will do summation of forces horizontal equal to 0 to the right forces to be positive. That is for member AF, I minus the 30 kilonewtons, I minus horizontal component will be 3/5 of AB, 83.333 equal to 0. So we will be having the axial force for member AF that will be equal to 80 kilonewtons, and this is under tension. Okay, for member AF. That is for joint A. Okay, this is an easy one. For example, if we are to proceed at joint F, so at joint F, forces are collinear. So let's say this is for member AF, and we have member EF. Okay, so we have the load, which is 60 kilonewtons, and I assume that the axial force for member BF will be upward. So as you can see, forces at joint F will be collinear, and if we have two forces are collinear, they are equal. So we have the axial force for member BF will be obviously equal to 60 kilonewtons, and this is obviously under tension. And the axial force for member EF should be equal to AF. And what is the axial force for member AF? That is 80 kilonewtons, also under tension. Okay, then we will proceed to at joint B. So we have at joint B, we have member AB, 83.333 compression. I'll be assuming that BC will be under compression. We have the member BF, that is 60 kilonewtons, under tension. I'll be assuming that BE will be under tension. This is by summation of forces, vertical equal to 0, upward forces to be positive. We have 83.333, vertical component is 4 over 5 minus 60 kilonewtons, then minus BE, vertical component is the same as 4 over 5 equal to 0. So you have the axial force for member BE. That will be equal to 8.333 kilonewtons, and this is under tension. Alright. So for member BE. Then we have for member BC. This is by summation of forces horizontal equal to 0, to the right forces to be positive. We have that 30 kilonewtons plus 83.333. Horizontal component is 3 over 5 plus the horizontal component of BE 8.333. Horizontal component is the same as 3 over 5 minus the axial force for member BC equal to 0. So let's compute for the axial force for member BC. Is equal to 84.9996. So let's say the axial force for member BC is approximately 85 kilonewtons, and this is under tension. Okay? And we have few members remaining left, so let's compute for those values. Okay, so here at joint E, so we have the 120 kilonewton load, so EF is 80 kilonewtons, we have BE is 8.333 tension. So we may have summation forces, vertical equal to 0, upward forces to be positive. That is 8.333, vertical component is 4 over 5 plus EC, then minus the 120 kilonewton load equal to 0. So we have the axial force for member EC is equal to 100. This is 113.333 kilonewtons, and this is under tension. Then by summation up, summation of forces horizontal for member DE, we have the summation of forces horizontal equal to 0, to the right forces to be positive. This is DE minus 80 kilonewtons minus horizontal component, this is 8.333. Horizontal component is 3/5 equal to 0. Axial force for member DE is equal to 84.9998. So let's say approximately 85 kilonewtons, and this is under tension. Okay, so we have the last member, that is at member joint D. So this is by summation of forces, vertical equal to 0, upward forces to be positive. So we have earlier the support reaction, 113.333. That is 113.333. This is minus. The axial force for CD, vertical component, is 4/5 of member CD equal to 0. So you have the axial force for member CD is equal to 141. This is 141.666 kilonewtons. And this is under compression. So we have the axial forces due to real loads. So next is we are to compute for the axial forces due to 1 unit load by replacing the redundant earlier. We replace it with a 1 unit load. So our next step is that we remove all the real loads acting on this truss. So initially we remove the horizontal reaction at D, that is the DH, that is the chosen redundant. We replace it with a 1 unit load. So if the direction of this 1 unit load is horizontal, that only means that we don't have a vertical reaction. dB is 0, or the same as the A vertical is also equal to 0. We have here, what will be the horizontal reaction at A? Summation of forces horizontal equal to 0. To the right forces to be positive. That is the 1 unit load minus the A horizontal equal to 0. Obviously, we have AH equal to 0. So this is A horizontal is equal to 0. If we are to analyze the entire frame starting at joint A, entire truss, so we have at joint A, since we have A vertical is equal to 0, we have A horizontal is equal to 1 unit. So it is obvious that the axial force for member AB should be also equal to 0, and member AF will have the same as 1. Since we don't have a horizontal, we don't have a vertical force, AF is equal to 1. Then again, at joint F, so at joint F, at joint F, we don't have a vertical load. We have only an axial force. F is equal to 1. So it only means that we have the axial force for member EF is equal to 1. And BF is equal to 0 since we don't have a vertical load. Then we proceed at joint A. So at joint A, we have EF is equal to 1. Again, we don't have a vertical force. So BE will be equal to 0, EC will be equal to 0, and D is equal to 1. So in the same way, if we have one horizontal, d vertical equal to 0, it only means that CD will also be equal to 0. And since there's no vertical force transferred by these intermediate members, okay, it only means that the axial force for member BC will be also equal to 0. So these are the axial forces for all the members due to the 1 unit load. Replacing the redundant DH with 1 unit load. So let us tabulate all the results. Okay, so we tabulate the axial force due to real load, the axial force for bar due to the unit load. So we need the product of the axial force due to real load, then the axial force due to unit load, that is the equivalent 1 unit replacement for DH. So obviously, we have these values. And for the product of the axial force, unit load, and the length, since we have 0 here, so this is 0, okay, we have 0, 0, then this is 85 times 1 times 3. So 85 times 3, that is equal to 200. We have positive 255. So don't forget the sign conventions. So axial force which are compression will be negative, then tension will be positive. So this is 80 times 3, we have 240. 80 times 3, the same as 240. 60 times 0, so this is 0. We have 0 and 0. So let us determine the summation. We need the summation of the axial force due to real load, unit load, length divided by, divided by A. So let us take the summation. That will be 255. 255 plus twice of 240. So that is equal to 735 over AE. This is the equivalent of our delta, the deflection of the truss due to real loads. So we have, how about this one? So since we have the unit load, axial force due to unit load times the axial force due to unit load times the length of the bar. So we have, since that is 0, this is 0, 0, 0. Okay, so that is the same as 1 times 1 times 3. That is the same as 3. We have 1, that is the same as u squared times the length. 1 times 1 times 3 is we have 3. 1 times 1 times 3 is the same as we have 3. This is 0, 0, 0. So these members will be, this will be equal to 0. So let us determine the summation. This is the summation of the axial force due to unit load multiplied the axial force due to unit load, the length. This is divided by AE. And that is equal to, as you can see, we have 3 plus 3 plus 3. That's equal to, we have, this is 9 divided by AE. And it's equal to our F. So if we are to recall our compatibility equation on the start of this video, that is the delta, deflection of the truss due to real load, plus the deflection of the truss due to the unit load multiplied by the redundant is equal to 0. This is 735 divided by AE, plus we have that is 9 divided by AE, multiplied by the redundant equal to 0. So we have the value of the redundant is now equal to 735 divided by 9. And that's equal to negative 81.66 7 kilonewtons. So what does this mean, the negative sign? So the negative sign indicates that we have, we have a wrong assumption of direction of the DH. So take note that our redundant is the horizontal reaction at joint D, or at this hinge at D, which means the correct direction of DH is equal to 81.667, and it should be, our assumed direction for DH is to the right, but its correct direction should be, it should be to the left. Okay? So 81.67 kilonewtons, that is to the left. The The horizontal reaction at hinge support at E. Then, if we have now the redundant, how to compute for the actual bar force. That is, the actual bar force S prime is equal to the actual force due to real loads plus the unit load or the actual force for members due to unit load. This is multiplied by the redundant. Okay, so that's compute for the actual forces or the actual bar forces. Okay, so we proceed with the computation of the actual bar forces for all members. For example, we have for member AB. Okay, so let's say this is the actual bar force for member AB is equal to, what is the actual force for member AB due to real load? That is, we have negative 83.333 plus, what is the actual force for member AB due to the unit load at joint D? That is 0 multiplied by the redundant 81.667. So obviously, the actual force for member AB is the same as negative 83.333 kilonewtons. So again, the negative sign indicates that member AB is under compression. Let's try for member DE. This is the actual force for member DE is equal to actual force due to real load. That is equal to 85 kilonewtons plus, what is the unit load for member DE? That is 1. So we have 1. This is multiplied by the redundant. Supposedly this is negative. This is negative 81.667. So we having the actual force for member DE, that is equal to, okay, we have 85. This is 85 multiplied by minus 81.667. That will give us the value of 3.333 kilonewtons, and if it is positive, it is under tension. Okay? So we have for member AB, this is negative 83.333. So since this is 0, for BC is also negative 85. If that is 0 for CD, that only means it is the same as negative 141.666. So all of these three are under compression. We compute for DE a while ago. It's equal to 3.333. Okay, how about for member EF? Okay, for EF, that is, we have 80 plus U is 1. Redundant is negative 81.667. And it's equal to negative 1. This is negative 1.667. For member AF, I think this is the same as negative 1.667. If this is 0 for member BF, that is the same as 60. If this is 0, the same as 113.333. And for BE, this is 0, the same as 8.333 meters. So these are the actual bar forces. This is our first example for the analysis of indeterminate truss using virtual work.